My name is Zahidul Islam and I am a student of Kangon University and I study at Department of Electronic Engineering, and today I will discuss chapter 3 of MMIC technology book, and the name of the chapter 3 is RFIC module design 1 MMIC amplifiers. To discuss the basic theory of MMIC amplifiers, firstly I will discuss with the DC bias induction topic, and we can see a figure. This figure shows typical FET IV curves and its operational bias points, and this figure number 3.1 shows different bias points 1, 2, 3, 4, and the first bias point is called noise point, and this time FET is operated at VGS voltage minus 3 volt, and here I represents, I already tell, noise point, but also this point is called low noise operating point. At point 2 the FET is operated with the VGS close to 0 voltage. VGS means grain source voltage will be 0 voltage in this case, and the point 3 is also called linearity, and this point is placed almost exactly in the middle of the IV curve, allowing the maximum linear output power to be achieved for class A operation. And point 4 is called efficiency point, and for higher efficiency, although the linearity will be degraded, the operating point IV can be used for class AB operation of the amplifier. There are many applications in which low DC current is more important than the ability of the device to operate at low drain voltages, and this is the best explained by studying the three-stage amplifier circuit diagram in the figure 3.4. There is a three stage 1, 2 and 3, and this is the source to drain DC bias connections, and is the matching. These amplifiers use both self biasing and stacked biasing technology. The drain current from the third stage of FET passes its source into drain of the second stage of FET, and then from the second stage FET source into the drain of the first stage FET. This is achieved by having the sources grounded at AC with decoupling capacitors and by using inductors to connect successive sources and drains at DC. This input, here we can detect output. This is the diagram of three-stage amplifier. The stability of an amplifier is very important considerations in the design and is decided based on the S parameter of the active device as well as matching and termination. Figure 3.5 shows the stability of circle on a Smith chart at the output plane and shadow region. Shadow regions and output plane in figure 3.5 is the stable region, and this is that means shadow region in the figure is the stable region. This region are stable, this region are stable region, where the figure 3.c shows the circle of unconditional stability, and here for unconditional stability any passive source or load can be expressed in this form, and these conditions have to meet here. And next I will discuss the methods for improving stability. There is a two method for improving stability: resistive loading and feedback method. Transistor stability can be improved by adding small series or large shunt resistance to the input or output as shown in figure 3.7, and the small resistance in series input or output, or large shunt resistance input or output. At feedback method, most amplifiers incorporate some form of feedback, and I will discuss later uh, feedback method again in next chapter. So right now we can see the resistive loading for stability, different configurations. From the figure we can clearly understand the resistive loading. Now I want to discuss the power gain equations. The power gain equations are very important for HBT configuration or any bipolar junction transistor configuration. The transducer power gain GT is denoted by GT, and GT equal power delivered to the load by power available from the source. That means GT is the ratio of PL by PABS, power delivered to the load and the power available from the source. And GP is another gain. GP also called the operation power gain. This one GT was the transducer power gain, but GP is called the operation power gain. It is the ratio of the power delivered to the load and the power input from the network. There is another power gain. This is called available power gain. Is defined as the ratio of power delivered to the network by power input from the source. We can clearly understand a diagram of the microwave amplifier. We can see there is a different network, output matching network and input matching network. Also I can see different route, input output here, and RL is the load and BS is the input signal, and RS is the series resistance with the source, and GS and GL is the gain parameter. Now I want to discuss the thermal noise. The definition of thermal noise is electronic noise generated by the thermal agitations of the electrons inside an electrical conductor at equilibrium. In other words, it means that the noise is always generated when a current is passed through the resistor. Thermal noise is referred to a multiple names. It may also be called Johnson-Nyquist noise. And thermal noise means a noise always generated when a current passes through the resistor. We can understand easily thermal noise from this figure 3.9, and thermal noise power equation Pn equal kT del F, where K is the Boltzmann's constant and T is the absolute temperature in Kelvin, and del F I is the noise bandwidth in Hertz over which the measurement is carried out. Now we also note our different noises, but I want to discuss here another three noise: short noise, popcorn noise, flicker noise. Briefly I will discuss short noise first. The short noise or Poisson's noise is a type of noise which can be modeled by a Poisson's process. In electronics, short noise originates from the discrete nature of electric charge. Two conditions must be satisfied for short noise to occur. There must be a direct current flow, and there also must be a potential barrier over which the charge carriers can hop. In case of popcorn noise is a type of electronic noise that can occur in semiconductor and ultra-thin gate oxide films. It is also called random telegraph noise, burst noise, impulse noise, bistable noise, or random telegraph signal noise. Finally, I will discuss the flicker noise. Flicker noise is a type of electronic noise with a 1/f. This is the ratio. That means this is the inverse of time period power spectral density. Here f is the frequency. It is therefore often referred to as 1 by f noise or pink noise. Though these terms have wider definitions, it occurs in almost all electronic devices and can show up with a variety of other effects such as impurities in a conductive channel, generations, a transistor due to base kind, and so on. This is a block diagram of Ku band low noise block down converter. Is denoted by L and B down converter, and this converter convert the RF signal into the IF signal, and IF amplifier is used here for amplifying the signal, and there is a filter also, and also the LNA converter circuit for first convert the RF signal into the another form of IF signal, then filtering, then mixture, finally amplifying, and then we get the IF signal. This is the block diagram only. Two-stage broadband IF amplifier design, another important factor for semiconductor and also for transistors field. The two-stage broadband IF amplifier was designed to obtain specific values of gain, bandwidth, and flatness. The amplifier schematics are shown in figure 3.11. The most normal topology is the use of resistors in series with matching circuit as fig 3.12. Figure 3.11 simplified schematics of amplifier. There is a two stage, one stage, and two stage, and different lossy matching. The lossy matchings have the input matching, inter-stage matching, and output matching to allow for a voltage divider bias to provide bias point stabilization. Each stage has a resistor with an established constant DC current, and it's a here input and output, and here is a established constant DC current with resistors if of is with each stage. In the emitter of the heterojunction bipolar transistor, probably this constant DC current is supplied with the resistors, and these resistors connect with the base and emitter of heterojunction bipolar transistor. It is a heterojunction bipolar transistor. It is also a heterojunction bipolar transistor. Now I will discuss the measurement section, and this slide represents two plot, and these two plot represent the simulation result and measurement results together with a error bar. And in this side x-axis there is a frequency in gigahertz, and this side there is a gain in decibel, and we can see the difference parameter variation with frequency and the gain. Different frequency changes, we can get different gain from experimental and simulations. These two are this results figure. Now we can see the block diagram of Ku band L and B as a super heterodyne front end. This area is called the super heterodyne font int, and is the IF amplifier. Here is the RF signal is applied, and the IF amplifier is amplified the signal. Then finally we will get the IF signal at the output. Now I will discuss briefly indium gallium phosphide heterojunction bipolar transistor and configurations. Is a schematic diagram of the cascade LNA with image reject notch, and this diagram is used the 6-inch indium gallium phosphate gallium arsenide high linearity heterojunction bipolar transistor technology. And the cascade the LNA design, there is some parameters, important parameters for notch, and the bias parts, that means the bias circuit of the cascade stage consists of R2, R3, Q6, Q7 and Q2 parameters, but the resonance frequency of the notch can given by others parameters, that means inductor capacitors have a relations with the notch frequency, and the notch frequency equal 1 by 2 pi root over L3 dot C4 plus C by 3 dot CB and divided by C4 plus C by 3 plus CB, and this is the final equation CB equal C7 dot CBR divided by C7 plus CBR, and this is the figure this that represent the junction capacitance variation as a function of the control voltage for the BC junction diodes. And there is x-axis the voltage and y-axis the junction capacitance, and different variation with the voltage, different junction capacitance we can measure. And it is the micro photograph of the fabricated Q band cascade LNA with a tunable image reject notch. This notch have a specific area 850 micrometer into 800 micrometer, and this another figure for the passband gain and the noise figure characteristics. This is the two measurement. One is this is a noise figure, and this is for the passband gain figure, and this figure 3.20 gain response of the cascade LNA, and it represents the gain response when the notch is off, and when the notch is on I can see a spike lower direction, and there is a two condition, notch off or notch on. This axis there is a frequency, and this axis we will get the gain in decibel. In case of the cascade LNA design, finally we will get some measurement results and also some experiment simulated result. But here the summary of the measurement result in this table: different parameters, supply voltage VCC, units B, LNA performance 3.06, consumptions milliampere 16, and passband gain 11.7 by 12.75 gigahertz. Notch off, notch on in two condition. Notch off, the decibel will be high 6.4, but in case of the notch on is a little bit lower 6.1. And we also know the important parameter, the noise figure. At 11.7 gigahertz in decibel, the LNA performance 0.25. As the case of the 12.22 gigahertz, the decibel linear LNA performance will be 1.9. This figure also shows the characteristics of gain, compressions, and output power as a function of RIF input power. at a specific frequency 12.22. At a specific frequency we can see the output power and input power variation. Output power and input power variation, and along with site at we also can measure the gain compression here together simultaneously from the figure. And this is a simple configurations of the three-stage power amplifier. Is stage 1, stage 2, stage 3, and stage 1 before stage 1 there is a input matching, then interstage matching, then again interstage matching, and finally output matching. And is the block diagram, and same thing this is with a schematic configuration: 3 stage, 1 stage, 2 stage, and 3 stage, and all are power amplifier. And it is a symbol or very basic schematic for a power amplifier. And the power amplifier have RF input power and RF output power, and upside and downside there is a DC power, PDC, DC power. And the power amplifier ultimately can be considered from the energy perspective as a component converting DC power from the supply PDC into microwave power output driven by input power. This process is schematically depicted. This is the power amplifier. The matching in case of the power amplifier is very important. A power amplifier can be designed by using the some basic matching principles already used for smaller signal designs, but with a power matched output that will not appear to be conjugated match. In figure 3.25, the power transfer characteristics of a class are amplifiers with two different output matching conditions. In this figure we can see and two line. One line is denoted by dotted. This is one for matching, another one is conjugated match. The compression characteristics for instance of conjugated match and the power match. The power match is a dotted curve and conjugated match for the solid line. And now I will discuss the power amplifier designed load pull method. Load pull method is very uh, important for power amplifier design. The design of power amplifier based on the load pull is the most empirical approach. In its basic form, an output tuner is adjusted to maximize the output power. Is the output tuner, there is also input tuner, but the if the tuner is removed and then its input impedance is measured on a network is analyzer. The stabilities of CDMA application, it is actually for CDMA applications. And input impedance and power measurement system, input impedance and power measurement systems, in input also output this system is exist. The power amplifier designs have some simulations or measurmental result. We can see from the figure and different figures. Figure 3.27, the maximum gain and S21 gain, and figure 3.2, the stability of CDMA applications, and figure 3.29, the load pull data regarding the characteristics of output power, and different parameters we can measure, we can see from the figure. This is a fabricated power amplifier, and we can see the image, different portions of power amplifier, and also the area is similar or previous one. and this is the measurement of PCB board for connection. Thank you.